Assalamu alaikum and greetings. In this video I will try to present you Savart's law, his method for calculating a magnetic field or magnetic flux density. I will sum up all the important things that I told in previous videos. So we have learned in previous videos, if we have a current, if we have a conductor with a current I, that this current creates a magnetic field. Lines of magnetic fields are presented with circles as shown here. The direction of magnetic fields is determined with the right hand rule, where we put our thumb of our right hand in the direction of current and our closed fingers, as we close them, they show us the direction of magnetic field. So we see that from this right hand the fingers goes this way from you to the table, and from this left side the fingers goes from the table to you. We already told in the previous video, because this is a circle, if we want to determine the direction at one point, because it's a circle, at every point the direction is a tangent to that circle. If we need to calculate a magnetic field at this point, the direction of a magnetic field is from you to the table, and we will present that as this way. And if we need, for example, to calculate at this point, the tangent is here, so the magnetic field, because this is a conductor, the magnetic field is from the table to you. Very important thing, if we need to calculate a magnetic field here, the magnetic field isn't pointed directly to you, because it is a tangent, and my circle, I don't calculate it here or here. I calculated somewhere I calculated somewhere in the middle, so the tangent moves on the circle. As I move during that circle, the tangent moves. So for example, if I need to calculate it here and my conductor is here, this is the tangent. It is pointed at some other direction. It is not pointed to you. It is pointed at other directions, and it has some other components of x, y, or z axis. But in most cases we will get this way. How can we calculate a magnetic field? Here is uniform formula, but this is simplified formula, and we will use this formula for calculating a magnetic field. Magnetic flux density. Magnetic flux density is equal to μ0, which is a constant for air, and it is 4p times 10 to the power of -7 times the current, sine phi2 minus sine phi1. We will see what are these angles, how do we determine them, divided with 4p times d, where d is the distance from the conductor. But is it any distance? No, it is a normal. This distance must be normal to a conductor. And this is the distance here in formula. So whenever we have a point in which we need to calculate a magnetic field, first we must draw a normal line to our conductor, and that normal line presents this d, the distance from our conductor. So here the magnetic field are concentrical circuits, and in dependence where do we need to calculate them. we will draw that magnetic field. The amplitude of magnetic field, as we can see from the formula, it depends from the current. If the current is constant, it depends from another pointer things, and that's the distance. So, if we increase the distance, we can see that this complete value is less. So our magnetic field or magnetic flux density is less. As we move away from a conductor, a magnetic field is weaker. As we are closer to a conductor, our magnetic field is stronger. So now I will show you how to use this formula to calculate a magnetic field. Few cases here, just. Case number 1. I have a conductor with length L with a current I. Very important for me, always the current must be given. If it's not given, ask them to give you, or ask for a permission that you choose what the direction of current will be. Because of this direction your calculations will be different. Why? Because magnetic field will have a different direction. Then, and it is said that we need to calculate a magnetic field, magnetic flux density at this point P. So, our first step is to draw a distance D, which is normal to this conductor. So, we will draw a distance D, and this is D, and it must be, remember, it must be normal to this conductor. Now, when we draw this distance P, D, we can get two angles. What do we do next? We take from this point where we need to calculate a magnetic field, magnetic flux density, draw a line to connect this point with this end of a conductor and this point with this end of a conductor. Now, you can very easily suppose what are these two angles from this formula. Those are, as we draw this distance which is normal to a conductor, we got, and this line, we got two angles. One is phi1, angle 1, and one is phi2. You can notate this and write, use alpha, beta, theta, whatever you want. But now, very important thing is this first angle and this second, or is it opposite? What determines which angle will be first? The current determines which angle will be first. So, on which angle the current firstly comes, that angle is first. We see this is the direction of current, so it means the current flows from the above to up. If current flows this way, we see this is the angle, first angle, phi1. And this is the angle phi2. So, for this case, what can be a problem with these assignments and calculations? The problem can be to find this in this angle. But you will find that using formula for sine. You have hypotenuse A, B, C, angle alpha, and we know from trigonometry, from math, that sinus alpha is equal the opposite cutted side of a triangle through hypotenuse. Cosine alpha is equal this in line cutted A through hypotenuse. Tangents alpha is equal sinus through cosine, which means B through divided with A, or opposite with this. So, using trigonometry, everything that we have learned from trigonometry from math, you will find this angle. And that is the most, in many assignments, the most difficult part. If you know the basic trigonometry, no problem. So here we will not, because we don't have the geometry of this problem, we will write this equation. But the other thing is that these angles, phi1 and phi2, can be positive and can be a negative. When it is positive, if this current enters at this normal, the angle is negative. So here for phi1, the current enters at this normal, so phi, it is a minus phi1. We will use a minus phi1 here. If it comes out from the normal of that angle, if the current comes out from the normal of that angle, then that angle is a positive, phi2. I will remember you from the trigonometry that sinus minus alpha is actually minus sinus alpha. Why? Because sinus is determined, we know this is cosine x on x-axis and y-axis. This is sinus y. And if we have a positive angle, for example this, the value of sinus in negative angle is the same, the amplitude is the same, but the negative value. Okay, here we can see that it is the same, but this is alpha, this is minus alpha. It is the same, but the negative value. So, our Biot-Savart's law for this case would be that B equals mu0 I for PD times sine phi2 minus sinus minus phi1. We already told that this minus sinus minus phi1 is actually minus sinus, and this minus is plus sine. So our magnetic field for this case will be sine phi2 plus sine phi1. So sine minus phi1 is minus sine, and this minus will give us a plus. Now, this is a conductor with finite with length m. Now, the second case we will analyze, and in many assignments you will have this case, that we have infinitely long conductor, infinitely long, with current I. Okay, we will draw the current in this direction. So first we need to determine the magnetic field for this conductor. Our thumb, we put it in the direction of current, and our closed fingers show the direction of magnetic field, and we will see that this is the direction of a magnetic field. So, once again, we need to calculate on a distance d, this magnetic field on a distance d. Okay. At this point, P. First, as I already told you, we must draw this distance d. It must be a normal to this conductor. So this is our distance d. Again, how can we find these two angles? We draw it from this point to the end of this side of the conductor and to the end of this side of the conductor. We see that we have two angles. We can visually see those two angles here also, so this is one angle, this is the other angle. Which is the first angle? We already told in this case that the current direction determines which angle is first. If the current enters on which angle it enters first, that is the first angle. We can see that the current doesn't flow from down to up, but it flows from up to down. This is the direction of current, you can see. So this is the first angle, phi1, and this is the second angle, phi2. Now, what is important is to determine what is the value of this angle. Remember that in this case we have infinitely long conductor. So, we don't know what is the angle, but let's try to solve it step by step, mathematically, using mathematical method logically. It is very important not to know the answer right away, but to use step by step to solve that problem. Okay, I don't know what is the value of this angle of phi1, phi2, but I will use a mathematical principle, method by method. And let's say I draw, this is my point D, I draw some length L. Okay, I will have phi1, phi2, some angles. What will happen if I increase this length? Okay, now I will have this case. Look what happened. It happened that my angle increased. What if I have a longer, even longer conductor? Once again, my angle will increase. So here we can logically conclude, if this I continue to increase this in infinite, this angle will increase, and it will have a maximum value of 90 degrees. It will be parallel to this if I go to the infinity. The same here is here. As I increase this length, I get larger and larger and larger angle, but I cannot get a larger than 19 degrees. So, in this case, phi1 that is equal 90 degrees on p1/2, and phi2 is equal also 90 degrees on p1/2. But now, very important thing is, as I told at the previous case, these angles can have a negative value. So how do we determine what determines will it be a positive or negative value? The current direction determines it. If current enters at this angle normal, then it is a negative value, so phi1 is minus p1/2. If it comes out from this normal of this angle, it is a positive value. So for this case, we will write, so this is our second case. our magnetic flux density will be equals mu0 I for PV sinus phi2 is p and a half or 90 degrees minus phi1 is minus p and a half or minus 90 degrees. We already said that we can write that as minus sine positive angle. This minus will give a plus, so it will be sinus p and a half. Sinus p and a half and sinus p and a half is 1 and 1, which means 1 plus 1 is 2. Times 2, this 2 and this 2 we can divide it, so this is it. And the unit is Tesla. Don't forget. You can lose maybe some points if you don't write the unit. And it is the unit that you can most easily remember. So, our magnetic field is equal to this. And this is very important. Why? Because at these assignments at the beginning, we will use Biot-Savart's law to calculate magnetic field for infinitely long conductor on point D. But as we move forward, as we continue with our assignments, we will consider to know this formula. For now, we will calculate it every time, but in the future, when we say we have an infinitely long conductor, remember that the magnetic field at the distance d or x or r from this conductor is this. So, please remember this formula. At the beginning you cannot use it, but after some time we will consider it that we can use it, that we know it and such. So, let's continue. Next cases. The next case is this. We have infinitely long conductor, but it starts from this point. And we need to calculate a magnetic flux density at this point here. So, once again, what we need to do is draw a distance from the conductor so it has a right angle. It is a normal. So this is distance d. The next step is to this point connect with this point. Okay, we will have that this is the current I. But what do we have now? As you can see, now we can visually see only one angle. And that's it. That's this angle. But we always must have two angles, phi1 and phi2. If we cannot see it visually, some of the angles or none of the angles, maybe only both angles are equal to 0. Or one of the angles is equals 0, and we will see that in this case. But here, okay, we usually can see only one angle, but which angle is that? Is it phi1 or phi2? What determines that? We said that which is the phi1 or phi2 angle determines the current direction. At which angle does the current first lead? Goes. So here we can see the current comes from the abdomen. So firstly was some angle that we don't see it, so this is the current comes out from the normal, so this is the angle phi 2. If the current, this current was this direction, I prime, so this current would firstly go at this angle, so in that case this would be phi 1 prime. In that case, because this is the first angle on which the current comes. But that's not the case. The case is this, so we will... Okay. But, what is the angle phi 2? Phi 2, because it said this is infinitely long conductor, but it starts from this point. So this is infinitely long conductor. Once again, we have from the previous case that this angle is 90 degrees. Because the current comes out from this normal, it has a positive value. But what happened? What is the value of angle phi 1? The value is 0 because we don't have it. Once again, we cannot see it. We cannot determine what that angle is. Okay, let's use again the previously shown mathematical principle. Let's solve step by step. Starting from what I know, coming to the answer that I don't know. So, let's say this is the point, this is a normal, this is angle phi 2, and this is angle phi 1. This is my point. But my case is this. So what happens with the angle phi 1? Let's use logic. What will happen if I shorten this conductor? Let's say this is the length of my conductor. What will happen? My angle will be this. If the conductor starts even after, at this point, my conductor is equal to this. So my first angle is this, then my angle is this, then my angle is this. So we can conclude and we can see that this angle tends, it goes to 0. So in this case, when it's completely parallel, at the beginning of this conductor, angle is 0. So our equation will be B equals minus 4PD times sinus phi 2 is 19 degrees, sinus phi 1 is 0, and let's remember that the sinus of 0 is 0, so we will not have this sinus, we will only have sinus of 19 degrees, and that is 1. That is 1. But the next thing is, if I have this point P here, it is under this. As you can see, I don't have any angle. So in this case, phi 1 is equal to phi 2 is equal to 0. So what will I have? I will have this, that phi B equals sinus 0 minus sinus 0, which is 0 and 0. So my magnetic field is equal to 0 at this point. But now, the next case is very interesting. If I have a conductor, again infinitely long conductor, but it starts at this point, and I need to calculate, this is, let's say, the current I, and I need to calculate. I will use this direction, and I need to calculate magnetic field, but not at this point, not at this, but at this here. It is lower than this, but it is at some distance, P. Now, the question is, I can come in the contradiction from what I said previously, that our first step is to draw a distance from the conductor, and at this distance, this drawing must be normal to a conductor. What will we do now? Okay, it cannot be normal to this conductor, but we will make a fictive. Imagine we will put an extra and draw this distance as a normal in accordance to this conductor. But what now happens? Now happens that I have two angles. First one is the beginning of a conductor, and the second is the end of a conductor. Let's remember, this point, from this point, one is the end, and one is the beginning. So this is one angle, this is second angle. Which one is the first or the second? We already said that the current determines. The current comes firstly to this angle. As you can see, if current flows from down to up. So this is angle phi1, and this is completely angle phi2. So in this case, what will we get? Phi1 angle. In this case, very interesting. Phi1, we said, if the current comes inside of this, it is a negative, but if it comes from this normal of this angle, it is a positive value. So here, phi1 is a positive value because the direction of a current, we are looking only at the direction of current, comes out from this normal of this angle. So for this case, phi1 is a positive. I will wrote it like this. It's an only positive value. Depending from this geometry, it will have some value. It will have some angle that you will determine. And phi2, second angle, also this is his normal. Both angles have the same normal. The current comes out from the normal, so it is also once again a positive value. But because it is an infinitely long conductor, once again we have here that it is 90 degrees. And you put this here. Also, I will show you this following. Once again, I have infinitely long conductor, that the conductor starts from this point and goes down, and the current is at this direction, once again, and we need to calculate at this point a magnetic field, magnetic flux density. Once again, I already told you, we must draw this distance, and so in the way that it is a normal to a conductor. We will imagine that this is a conductor, this is a normal. So our first angle is this point and the beginning of a conductor, the second angle is this point and end of a conductor. So this is our first one angle and this is our second angle. But now the question is, which will be the first, which will be the second? Once again, the current direction determines that. Here we can see the current comes from here, and what is the angle which it comes first? It is this angle. So this big angle is phi1, and this small angle is phi2. So now let's determine phi1. Okay, now is it a positive value or a negative value? because the current enters this normal of an angle, we know that it is a negative value. So it is a minus phi1, because it is infinitely long conductor. Once again, it is 19 degrees. And phi2 is this, and also this is its normal, and the current also enters the normal, so it is a minus this angle. Mathematically this is incorrect, but this is just to show you, will you take a positive value of an angle or a negative value of an angle, because phi1 can never be equal to minus phi1. We could use some other notation, but it is very important for me to physically be clear when are you taking a positive or a negative value. So, in this case, we would have a magnetic field density sinus phi2. Phi2 is minus phi2. So this is a minus sinus phi2, using once again this. Also here I have minus sinus phi1. Phi1 is minus 90 degrees, so this minus, I will use this, it is a minus sinus, and this sinus will be plus sinus phi and a half. And we calculated. And our last case is if we have a circle with diameter r and which flow the current I, so this is the current I, and we need to calculate a magnetic field at the center of a circle. In this case, the magnetic field at the center of a circle, we will write that as BCC, center circle, is equal to μ0 I over 2R, where R is this. Very important. How do we determine the magnetic flux density or magnetic field direction? We can once again determine it by the right hand. We put the right hand thumb in a direction of a current, and my figures will show the direction of magnetic field. We can see that from this side to the left, in accordance to this conductor, the field has a direction from a table to you, and from this side it has a direction from you to the table. So here it has this from the table to you, and here, if we come to this point, we will get the same. If we look at this part of a conductor, we will always come to the same conclusion. So in circles, magnetic field created from every part of a circle has a same direction, and they are summed up, and we have our resultant magnetic field here. The other way to determine this is with the right hand rule, where we close our fingers, fist, in the direction of our current, and our thumb says what is the direction of magnetic field determines. So in this case, I'm closing in the direction of current, and my thumb tells us what is the direction of magnetic field. Is from the table to you here inside. If the current was at this direction, at opposite direction, so I cannot close my fingers this way. I need to close it this way. you can see that my thumb is directed from you to the table. So in this case, my magnetic field would have this direction. So that's it. Now, using all these rules, we will simply solve all our problems and calculations. Thank you for watching, and I hope we will see each other in the next video. Best regards.